Ice cube. It's a neutrino detector located in the South Pole, Antarctica. It is the world's largest neutrino detector and records interactions and studies neutrinos. The construction started in 2005 and ended in 2011, so it's a fairly recent project. And it was very expensive, costed $279 million US dollars. It was based on a pilot project called the Antarctic Muon and Neutrino Detection Array, and also known as AMANDA. Many people from the AMANDA project are now part of the IceCube collaboration. Currently, the collaboration includes people from 43 institutions in 12 countries. So why is this built in Antarctica? The ice in Antarctica shelters the observatory from interference. And there are things called domes in there, which I'll get to later. But before I continue, I'll show you a video as an overview of what this is.
Hi everybody, my name is Casey O'Hara and I'm here to introduce you to the IceCube Neutrino Observatory. This will be the world's largest telescope. It's currently being built at the South Pole, and it will allow us to study the universe by looking at neutrinos. Well, the first question might be, just what the heck is a neutrino anyway? Well, it's not a nutria, that's a kind of rodent. It's not a neutron, it's not Jimmy Neutron. It's not even something we've ever even seen in the world before. It's not even what we consider regular matter. So what do I mean by regular matter? Well, everything we experience every day, such as this pen, this dime, candy bars, you, me, everything is regular matter. It's all made of atoms. So atoms, as you might remember if you were paying attention in chemistry class, are made up of positively charged protons and uncharged neutrons, not the same as the neutrino, that make up the nucleus of the atom. And then electrons with a negative charge go around in an orbit around the nucleus. And because of these positive and negative charges, there's forces that act between the protons and the electrons to hold the whole atom together. But neutrinos don't act the same way. A neutrino has no electrical charge on it, so therefore no electrical forces act on it. So the neutrino passes right through regular matter, also known as atoms, like it's not even there. So neutrinos pretty much go through everything: walls, floors, us, the earth, the sun, everything. But this also means they'll go right through any sensor or detector we could ever build. Well, so how can we detect these neutrinos if they just go right through everything? Well, it turns out that sometimes, very rarely, like one chance in a million, billion, a neutrino interacts with an atom. And when that happens, we can detect the bits and pieces that come out of the collision. Okay, so here's an atom. It's made of protons, neutrons, electrons, regular matter. And here comes a neutrino. It hits, and then a new particle pops out. This particle is called a muon. Let's see the instant replay. Neutrino comes in, muon comes out. Now when a muon goes through a clear material, or medium, like glass, water, or ice, it leaves a trail of light behind it, like the wake of a speedboat. This is called Cherenkov radiation, and that trail of light tells us about the muon, which then tells us about the neutrino. So now we can detect neutrinos. So how does the IceCube neutrino detector work then? Well, instead of water for our clear material, like we've used in other recent projects around the world, our clear material, we can use ice. No, not otter pops. Yeah, that's better. And so where can we find a lot of ice? There we go, the South Pole. Alright, here we are at the South Pole. Look around. Nothing as far as the eye can see, nothing but ice. The ice cap there at the South Pole is 3 kilometers thick. And of course that means it's cold. It's time to put on a parka, maybe some gloves. Yeah, that's much better. Alright, now we're going to drill down into the ice. We're going to drill down to a total depth of about 2.5 kilometers. It's about 1.5 miles. Next, we're going to place a string of light sensors, starting 1.5 kilometers down and extending all the way to the bottom of our hole, a full kilometer. And in this string, we're going to place a total of 60 sensors. But I'm too lazy to draw it. So, what's better than a string of sensors? Lots of strings of sensors. The final project is going to use about 70 strings, each with 60 sensors, for a total of lots. I'm definitely going to need a bigger drill. Now, using this array of sensors, depending on which sensors are triggered in which order, tells us about the neutrino's direction and the neutrino's energy. Now, by studying these neutrinos from out in the universe, we can learn about amazing celestial events like supernovas, black holes, and gamma ray bursts, without even having to leave our comfortable home planet. Now, comfortable is a relative term. Well, I hope you enjoyed my little movie. You can find out.
Okay. So, here's what the center looks like. Remember in the video that we just watched, they talked about light sensors? Those are called DOMs, or digital optical modules. They're basketball sized and they are 1.5 to 2.5 kilometers deep in the ice. Okay, so they use hot water drills to put the DOMs in. And the hot water drill, there are two drills. The first drill is a lighter drill that drills through the snow, and the second drill drills through the hard ice. The drills take 24 hours to drill through the ice and snow and 10 hours to resurface. As you can recall, there are over 5,160 DOMs in the ice and an additional 344 on top of the snow. So these are the strings of the DOMs, and that is the comparison with the with Ice Cube and the Eiffel Tower. And the second picture is how a neutrino going through the DOMs and how the DOMs pick up the data from the neutrino. Now I'll talk about neutrinos again. They are almost massless subatomic particles that are formed from violent events such as exploding stars, gamma ray bursts, and radioactive decay. Trillions of neutrinos bombard Earth every second, but nearly all of them pass through because they are almost massless. Neutrinos are not neutrons. Neutrons have a neutral charge, but neutrinos have no charge. Excuse me. So neutrinos pass through regular matter, like Earth and tables, and are not affected by forces that hold other things together. Remember that there are forces between protons and electrons, and those forces do not affect neutrinos. Very rarely a neutrino crashes into a nucleus, and when that happens, we can detect the pieces from the crash. When a neutrino and an atom collide, a muon is formed. And as you can see here, this blue light triangle thing is the muon. And I'll expand more on that later. A muon is 200 times heavier than an electron and travels almost as fast as light. It makes up most of the cosmic radiation that gets to the Earth's surface. When a muon travels through something transparent, it leaves a trail of light. The trail of light is in the shape of a hollow cone and moves like a wave. From the light wave, we can learn more about the muon, which gives us information about the neutrino that collided. So Ice Cube uses the ice at the South Pole as the clear material to detect the waves of light from muons. Muons carry information about where they come from. And since, remember that neutrinos are almost massless particles that can travel through regular matter, they can come from faraway galaxies. So if we study muons from neutrinos, we can possibly detect different galaxies and stuff like catastrophic events. So that is Big Bird. Oh, no, never mind. This is also data from the Ice Cube Observatory. And this is, this diagram, or this picture explains the muon cone. So the cone is called Cherenkov radiation that is produced from a muon. Oops. And here's a video that tells more about the muons when neutrinos hit.
Here is a neutrino colliding with the water molecule of the aromatic ice. This collision breaks the nucleus apart, and the neutrino converts to a muon, which is basically a heavy electron. From the side, you can see another view of the muon's birth. This particular muon will be picked up by the detectors. Muons are able to travel several kilometers through the ice. You can recognize a muon that is traveling at nearly the speed of light by a cone of light that follows it. This cone is similar to a boat creating waves behind itself. Looking inside the light cone, you can see its structure. This light is known as Cherenkov radiation. The muon emits very faint blue light rays outward from its sides. Taken together, all these emitted rays form a hollow cone behind the muon.
So those circles
In the
are the
darkness
DOMs,
of
the light
Antarctic
sensors?
ice, this glow can be detected up to 100 meters away. The Amanda detector, frozen in a depth of 1,500 to 2,000 meters, is optimized in order to see this light. Amanda is built out of powerful light sensors which are packed into pressure-resistant glass spheres. Several hundred of these, attached to steel cables, have been placed more than a mile deep into the ice of the South Pole, where they watch for the faint signals from fast-moving particles. When a muon flies through the Amanda detector, each light sensor registers the passing cone of light within 1 billionth of a second. The sensors convert the light into electrical signals, which travel to computers at the ice surface. Scientists at the South Pole Amanda Center supervise the data recording and do initial
This is an
analysis.
older video from 2007.
Complex computer programs investigate the chronological order and intensity of the signals. From this information, scientists can calculate the most important information for any telescope, which direction the initial neutrino came from. Several hundred neutrino reactions have been detected in trial phases. In January 2000, scientists and engineers were able to finish the second phase of Amanda's expansion.
So now the
There are now
observatory is
670
much
light
bigger
sensors in
than
the ice,
what you see
and
right
in
now.
a few years, a much larger telescope with 5,000 light sensors will be built.
Here's 10 milliseconds slowed down to 10 seconds of data collected. So remember that those tiny circle things are the DOMs, or digital optical modules, that detect the muons. This is Big Bird. So it's so far the highest energy neutrino, and it has been detected a few times throughout 2011 and 2012. So in the end, why do we want to learn about neutrinos, and why do we have the Neutrino Observatory? Well, if we learn more about neutrinos, we can also learn more about supernovas, black holes, gamma ray bursts, cosmic rays, and different galaxies, since neutrinos are born from those events. We can learn where those things are, and we can also review why and how neutrinos change shape, and how they're made, because they're almost massless subatomic particles. It's also a very good tool to find out more about black holes. Thank you.